Okay, good morning, guys. In the previous lecture, I was able to derive the expression for natural frequency for a typical spring mass system. I've ignored damping. Generally, for most of the analysis, you can ignore damping for ease of analysis. So, continuing from where I have stopped with the natural frequency expression, we will try to apply the finite element technique to derive the equation of motion, formulate the equation of motion. In finite element methods, we use what we call it as the Lagrangian. Lagrangian is a mechanics approach. Lagrangian approach. It's a function which consists of displacements with time derivatives. So this is defined as Lagrangian is defined as L is equal to T minus pi. Okay, where T indicates the kinetic energy and pi is the potential energy. Using the variational principle called Hamilton's principle, for any arbitrary time interval from t1 to t2, the state of motion of a body extremizes the functional function of a function. I is integral of t1 to t2 LDT Lagrangian. Lagrangian is a function. As I said, it's widely used in dynamic problems to characterize dynamic system. Lagrangian is used. Okay, so this is the expression. If L can be expressed in terms of generalized coordinates, generalized variables, sorry, u1, u2, u3, and u1 dot, u2 dot, etc., where ui is the time derivative, displacement with respect to time, that is velocity component. Then the equation of motion is given by a typical d by dt of del L by del U I dot minus del L by del UI equals 0. This is typical variational calculus approach. Okay, this we are familiar even in structural problems. The solution of which leads to this particular equation, which is I equals 1 to n. Now, typically to derive the equation of motion, formulate the equation of motion, we'll consider a 2-degree freedom system, spring, mass, two masses, two springs, displacement x1, x2 imparted to mass 1 and mass 2. So using Lagrangian, we'll try to find the kinetic energy and potential energy expression first. Okay, just try to observe here. Kinetic and potential energy, the terms T, as I said in the previous expression, L is T minus pi, T is kinetic energy. Look at this. The kinetic energy is half mv square. V square is the derivative term, x1 dot square half m2 v2 square. Two masses are there imparting two components of kinetic energy, the summation of which total kinetic energy half m1 x1 dot square plus half m2 x2 dot square. Similarly, potential energy for a spring, which is a restoring force, that is kx, potential energy is half kx1 square ku. Ku is the spring force, we call it as spring force. Okay, so strain energy term, that is half k1 x1 square plus half k2 x2 minus x1 whole square. So this is the total potential energy. Substituting in the Lagrange expression, we will get this particular term. Okay, these terms from the previous kinetic and potential energy expression. Now once you substitute in the equation of motion the variational approach, you will be able to get this term. What is d by dt of del L by del x1 dot? You do the del L by del x1 dot, you will get m1 x1 dot minus del L by del x1. You do the take the derivative of x1 del x1 del L by del x1. We will get x1. This is a partial derivative, mind you. It's not full derivative, so it obviously x2 term becomes 0. So here it is k1 x1, then it is k2 into x2 minus x1. Look at this, del L by del x1. Of course, these are all x2 dot and x1 dot. It will not come into picture. Here I will be doing this particular expression. I will get the terms. From here I will get these terms. Now if I do this dy dt of mx m1 x1 dot, of course x1 dot is nothing but dx by dt. So it becomes x1 double dot, the derivative of velocity component, that is the acceleration component. Similarly, simplification will lead to equation number 1. Similarly, you import this particular equation for variational calculus expression on the same Lagrange for x2 dot consisting of the x2 dot term. So you will be getting this equation number 2, simplify it and try to write in the matrix form. You will get this particular equation. See how it resembles. It is resembling in the form of mx double dot plus kx equals 0. This entire thing is stiffness matrix. This is called mass matrix. So in case of structural problems, static problems, you are very familiar with this stiffness matrix. Kx equals F. Ku equals F. Here the equation of motion is zero because you are considering for the typical case free vibration. To understand the vibration, you start with free vibration, then go to different kinds of forced vibration, and other kinds of advanced vibration, transient and other kinds of vibration analysis. This is M1 0 0 M2. This is mass matrix, mass component coming into picture. So totally comprising of the equation of motion for an undamped free vibration in the form of matrices. This is where you can bring the FEM in or numerical technique to solve vibration problems with mass matrix playing a significant role. You can just express what is x double dot here, inertia effect, so the acceleration vector, then x is the displacement vector. Now, if you want to solve for this, typically we'll assume simple harmonic motion. To start with x is x sine omega t, take the derivative of it, x dot, you will get this expression, just differentiation of the x with respect to time domain t. Then again you differentiate, you will get x double dot acceleration component. It's called with mass, we call it as inertia component. Okay, this with spring you call it as restoring force. So once you simplify it, it is almost coming back to the same expression. Okay, the acceleration component is minus omega square times the displacement. Now coming back to the typical equation of motion in mass and stiffness form, you'll do resubstitute this equation for x double dot, mx double dot, you have this term mx double dot. I'll substitute for x double dot this particular expression minus x omega square sine omega t plus k into x is x sine omega t equals 0. Simplify further, you will get the expression for kx equals omega square mx. Put lambda, see, look at this here. Kx is equal to sine omega t will get cancelled. We'll get minus omega square, go to the other RHS portion, you will get plus omega square m into x. Now put the lambda as omega square, okay, then you will be getting kx is lambda omega x, or you take the other side, you will get k minus lambda m into x is equal to 0. Okay, this is a typical equation which you obtain, where x is called eigenvector representing the vibration mode and corresponding to eigenvalue lambda. Lambda is the square of the frequency. Okay, the eigenvalue is the square of the circular natural frequency omega. Omega n is 2 pi fn, well-known physics equation which you are familiar with your simple school physics. Now coming back to the above equation 1 is now an eigen problem. We call it as k minus lambda m into x is called eigen problem in mathematics. For a non-trivial solution of the above equation, it is necessary that the determinant of the coefficients will lead to polynomial lambda of order n. Okay, you will get different values for lambda of order n. This polynomial equation will have n roots like lambda 1, lambda 2, lambda 3, that is different natural frequencies. That is omega square value. Okay, then by substituting an eigenvalue lambda I back into the previous equation, above equation, using direct or iterative method, you will get this particular expression k minus lambda I into m into x equals 0, which is a set of algebraic equation. Solving it for the unknown x, a vector denoted by x superscript I can be obtained, which is nothing but eigenvector, which is going to give the different mode shapes for a given frequency that satisfies the following condition: k minus lambda I into m equals 0. Now coming back to what we call it as a very important analysis, so engineers will do is in the beginning we call it as modal analysis, the free vibration analysis. So modal analysis is one of the powerful tool to identify the dynamic behavior of the structure or components. As what do you mean by modal analysis? All of you are aware every structure vibrates with high amplitude of vibration at its resonance frequency. Whenever the natural frequency coincides with the excitation frequency, vice versa, there is a very high amplitude of vibration. We call it as resonance. It is important to know the modal parameters like resonant frequency, mode shapes, and damping characteristics of the structure at different operating conditions for improving its strength and reliability at the design stage. So, as a dynamic, analysis, as a engineer performing dynamic analysis, one should be aware of the various mode shapes, the effects of natural, the frequencies on the given particular structure. Okay, so this is very very important in order to characterize the damping, the dynamic characteristics of the problem or the structure. What is a mode shape? Mode shapes are the shapes in which components deform when applied dynamic loads of varying frequencies. This typically indicates the shapes at which the typical structure vibrates. You'll get different shapes in beams. I'll demonstrate this in one very interesting video I'll be sharing with you. Okay, where you can easily see the mode shapes for different kinds of frequencies and applied with different varying frequencies. The mode shapes tells us which region would experience high stresses if deformed. Shape is similar to mode shape. The output we get in commercial FE packages, what they use in industries, by doing modal analysis, include natural frequencies and mode shapes. You can see a typical mode shapes for a cantilever beam here. Okay, you can see the different mode shapes, right? So apart from that, so we have two matrices one should be aware of. As I said in the previous session, the mass matrix do play a significant role in case of vibration problems. There are two kinds of mass matrix widely adopted: consistent mass matrix and lumped mass matrix. In case of consistent mass matrix, when the entire mass of a system is evenly distributed over its length, it is known as consistent mass. This I will be deriving few expression on this in the next session. Okay, in consistent mass system, same shape functions are used for both stiffness and mass matrix. Look at this. This is why it is called consistent mass matrix. Same shape functions are used for both stiffness and mass matrix. I will show you this particular technique of deriving the consistent mass matrix for different elements like bar or truss. It's a popular choice widely used in dynamic analysis. This consistent mass matrix yield more accurate results for typical structures like beams. There is another kind of mass matrix widely adopted by practicing engineers. They are called lumped mass matrix. Here, total mass is distributed equally to the nodes. Lumped mass matrix generally contain diagonal elements, and the natural frequency obtained from lumped mass techniques are lower than the exact values. Typical lumped mass matrix I've written for a truss element. Of course, I'll be deriving the consistent mass matrix for bar and truss in the next session. Okay, thank you very much, guys.